Introducing AUL, a project for SCR 502 at ASU during the spring semester of 2016, created by Kanika, Caitlin, and Mina. Let's go over the basic overview of AUL. AUL stands for Another Useless Language. AUL implements delayed evaluation, and our project includes a high level and an intermediate level of our language. The file name extension for AUL is clearly .aul, and AUL was built with Antler 4.4 on both PC and Mac. We also used Eclipse and Sublime during the creation process of our project. There were 4 main steps that we went through as a team to create our language. First and foremost, we created a simple grammar using EBNF notation. We then used Antler 4.4 in the Eclipse IDE to implement a base listener class. This base listener class was generated automatically by Antler 4. We simply then extended the base listener class and wrote the translation process within that class in order to translate a high-level program to an intermediate-level version of the program. Immediately thereafter, we created our runtime using Java. Here's a snippet of the OWL grammar. As you can see, any OWL program begins with the root of this grammar. The root then proceeds to the program. The program consists of the keyword prog_start, assignment statement, a function declaration block, a main function, and concludes with the token prog_end. You can see on the bottom left of this slide that the main function consists of the token main and then a block. On the bottom right hand side of this slide, you can see that a block consists of the opening curly brace, any number of statements or expressions, and ends with a curly brace. You can also see some of the statements that we have included in our grammar. Further on in the grammar, which is not displayed on this slide, we have a rule called statement, and we list all of the various statements that are allowed as valid statements in our program. However, on this slide, on the right-hand side, you can see that we currently have an if statement and an else statement, as well as a while statement. You can also see on the top right-hand side, we have our function declaration block, which consists of any number of function declarations. OWL currently has built-in support for 2 data types, and those would be integer and Boolean. Why don't we take a look at some of the basic operations that can be performed in OWL? For example, on the left-hand side, we can see some examples of an assignment statement. Not only does this statement do assignment, but this also does declaration. In order to declare and assign, let's say, an integer x to 15, we would need to write integer with a capital I, the variable name x, the equal sign, and then the number 15. It's the exact same process to assign a Boolean, except the keyword is boo with a capital B, your Boolean name for your variable, and then the equal sign followed by the word true or false. In order to do arithmetic operations, you need to write print_num, and then within the parentheses, put the expression that you want evaluated. OWL also supports parameterized functions. On the left-hand side, you can see the high-level version of our program, and on the right-hand side, you can see the intermediate level version of our program. This example takes in an integer as an input, and in our main function, we're calling it. This is a really simple display function that simply prints out whatever number you give it. Currently, OWL supports one decision statement, and that's the if-else statement. The if-else statement takes the keyword if, followed by the expression to be evaluated within 2 parentheses, and then in curly braces we have the statement to be executed if the condition evaluates to true. If you want to have statements evaluated if the condition is found to be false, you would then use the keyword else, and within the curly braces, put those statements that you want executed. In OWL, loops are implemented using flags whose value is set depending on true and false of the given condition. The OWL language also currently supports a while loop, with the main difference being that we've called our loop when instead of while. So when a condition is evaluated as true, and this includes being continuously evaluated as true, then the statement inside of the curly braces will continuously be executed. Now, we're well aware that this slide shows an infinite loop, but OWL does support adding another statement within those curly braces in order to make some kind of arithmetic statement that evaluates out where your condition now becomes false and the loop ends execution. The built-in data structure that OWL currently supports is a stack. The stack comes with built-in push and pop operations. On this slide, we have a high-level implementation of a stack, and on the right-hand side, you can see the intermediate level representation of that same stack. Here's a really quick look at a calculator program that was written using OWL. Now, this isn't to say it's an actual calculator with a GUI or anything, but it simply shows all of the 4 arithmetic operations that are allowed in OWL, such as subtraction, division, multiplication, and addition. On the top right-hand side of this slide, you can see the actual .aul file that was written. And on the bottom right-hand side of this slide, you can actually see the real genuine output that comes from running our runtime. The nice thing about us using AUL 4.4 is that we're able to generate a parse tree for any file that we write in the OWL language with our OWL grammar. Here's an example of a parse tree that was generated for a simple calculator program. As you can see here, the program parses correctly through the root and then to program. Within our program, we have that pstart and pend token that begins and ends our program. And in between those, we have our assignment statement. Initially, we have an integer I that we assign to 20. We have our function declaration block. Well, in this case, we have none. We have our main function, which consists of the keyword main followed by a block. If you recall from that little snippet of our grammar, a block consists of curly braces, and within those curly braces, any number of statements or expressions. In this case, we have 4 statements. There are 4 function calls, and each function call includes the keyword print num, and then an expression within parentheses. In this case, we have expressions allowed to be equal to just numbers as well. So this is why for each expression that's within the parentheses after print num, you see 2 more expressions. In this case, you have 10 minus 2. Well, 10 and 2 in that case are both expressions in of themselves just for being numbers. This allowed us the most flexibility in our grammar. The nice thing is that for every program we get, we have a parse tree generated. Creating these parse trees aided us a lot in diagnosing problems and bugs within our grammar and within our code. Let's take a quick look at what a recursive function written in OWL looks like. Recursion in OWL is where a function calls itself and returns out of the program only when the terminating if condition is satisfied. A function is only called when the call keyword is encountered. In this example, we have the high-level code where we've defined a custom function called display. It takes 2 variables, and we're calling that function in our main function. You can see that in the if-else portion of our display function that there is a recursive call within the else portion. Let's very quickly go through a sample program from start to finish in OWL. The first step is to create a file written in the AUL language. In this case, this is our calculator file. As you can see, we have our subtraction, division, multiplication, and addition. Let's go ahead and save this as example.aul. Next, we're going to run the AUL runner.java file. If you're on a Mac, you may need to change the file path for both of these files here in blue. But if you're running a Windows computer, then you'll be fine and you won't need to change anything. Next, we see the actual generated intermediate code. This code will be printed out to you in the console. It will also be put into the example intermediate 1 file that's included in the ALU runner.java file. And now what you want to do is actually just run your runtime. The runtime for OWL is implemented in Java. It takes as input the intermediate code file and, depending on various cases encountered, produces the output. For our project, we've used a hash map to implement a symbol table to depict scoping. The program starts execution in the main and then executes each statement one by one. Here's the output that you would get after running that runtime. This is your translated and completely executed OWL program. Let's run through that example together. Here's a really quick overview of our grammar. You can see here that these are the files generated using AUL 4.4. This base listener class is what's called for every single rule within our grammar. We extended that class to ALUhelper.java, and we actually ended up writing all the code to translate from the high level to the intermediate level in this AULhelper.java file. Here's the calculator example that we made. You can see those 4 arithmetic operations in there. And then here's our runner file. This is what actually makes our lexer and our parser, and lexes and parses through whatever OWL file you feed it. It also outputs the intermediate code to that example intermediate 1 file. Here's a brief look at our runtime. You can see that we've used a switch statement and flags to make sure that we go line by line through our main function. At the bottom here, you can see the actual output from running that runtime file given the example.aul file.